Today, we're actually going to go down a little interesting path. We're going to talk about term rewriting, but not because term rewriting is actually the topic of this talk. The fact is that term rewriting is going to cause us to write certain kinds of programs, which are going to be very interesting and constructed unusually. Okay, and so I think that I want you to see the structure of the programs actually as being the content that we're trying to pass along here. In any case, there are these term rewriting systems that are quite interesting and useful. That you often do some algebraic simplifications in terms of them. For example, over there you see what you see is the distributive law of multiplication over addition. And it's written in, so you can see it goes both ways. That's not very important here. Term rewriting systems are things that take complicated expressions and make other more complicated or less complicated expressions by doing substitutions of parts for equal parts by some definition of equal. Okay, and that's all that really we're talking about there. Usually they're made out of pieces that are these parts. There's a pattern matcher, a skeleton instantiator. That is, the pattern matcher matches, says whether or not the rule, in some sense, matches some sub-expression you're looking for, and the skeleton is the thing that gets replaced by, with the appropriate variables in the skeleton, replaced by things that were picked up from matching the rule, the pattern. And then these are joined together in pattern skeleton rules, and then there's something that controls how this is done. There's a controlling system. And actually, the place I want to start today is the pattern matcher, and the reason is because that's going to show the interesting property that I want to get across here. So there, of course, because we're in the Lisp world, I'm going to make my patterns in terms of prefix notation. So as we're going to be matching what look like Lisp expressions. This is a thing that matches the product of A and the sum of B and C, where those are A, B, and C are syntactic variables. They've been designated or indicated by having a question mark here, saying this is a variable rather than a constant, whereas the product here is a constant. Okay, and so you see here the left-hand side and the right-hand side of the distributive law written out that way. Of course, in any reasonable system where people actually want to use it, there might be some abbreviation where this becomes part of the name or anything like that. But this is just to illustrate what's going on. We're doing the simplest stuff. Okay? So thank you. We found some black. Okay. We'll see if we need it today. Okay. How come the thing didn't go to the next? Oh, there it goes. Okay. So, for example, then they will say, how is the matching going to be done? Well, supposing we're looking at things like the product of cosine and exponentiation, and the product of cosine and sine. Okay, so that's cosine x times e to the y plus cosine x times sine z. Supposing that was the thing we're trying to match against this distributed out product. Then these things should match with A being cosine x, B being the exponentiate e to the y, and C being sine z. Okay, that's what this should have been. And the fact that these two A's are the same is fairly critical. So that's the constraint here that says if I had the same pattern but tried to match it against this fellow, it shouldn't match because this object is not equal to this one unless we assume x is equal to x plus y, which means we might be solving some equations. That may be possible, but on the surface today, I'm not doing anything as complicated as unification or even more extreme versions than that of solving equations, which is what that really is. Where's my unification person here? Somebody was giving me a hard time yesterday about Prolog. Okay? Okay, well, fine. He's apparently either hiding or not here. Okay, so we'll also need variables. Yes. Okay, well, one of the problems we have is things like sine square x in the traditional notation plus cosine square x is 1. Okay, that's a nice thing to be able to simplify. But of course, there might be other things in here, like the sum of 32, and this might have a 53x plus, and so on. And I'd like that simplified down to 53x plus 33. Okay? Because I'd like that 1 to come out. And of course, that means I have to be able to catch things that have maybe other stuff in between. 32 plus 1 sine squared plus cosine squared. Oh, you're right. Yeah.
Equals 1. Yes.
Equals 1. I'm sorry. Equals 1.
Thank you.
Right. Sorry. You're right. Okay. You're right that it was 32 if I were doing the subtraction. Okay. So the point is I have to invent a kind of variable that will gobble up lots of stuff. These are called segment variables. And I'm sure many of you have done this sort of thing before. So I'm not giving you any new stuff. I'm just introducing you to the notation we'll be using here. Okay. And so there are three other variables here, T1, T2, and for some reason T3 is here rather than carriage return and put under here. That means I did a lousy job of pretty printing. But that means that if I see a sine x squared and cosine x squared in a sum, then I should be able to collect all the other terms together and put a 1 there. I add a 1 in there. So that's the sort of rules I might be interested in having. Okay? Now, once we have segment variables, there are complicated things that happen. So, for example, if I have this strange pattern, A followed by any number of things which we will call X, followed by Y, any number of things called Y, followed by another any number of things called X, then followed by a C, I may have to match something like this, and there are actually 3 possible matches. Do you see them?
Where does the D go?
Oh, that was a typo. Whoops. Whoops, typo, because okay, that should be a D at the end here. That should be a D. Okay? Obviously, I was editing my slide and blew it. The reason why that should be, if you all see the D, and if this were a document camera, I would have put the line in and you would see the D. If you see the D here, there are 3 ways it could match. For example, it could be that X could be the empty pile of stuff, okay, in which case the Y is everything between here and here. Or X could be a BC, and there's a BC over here, and then the BCBC, this one in the middle, would be the Y. And the other possibility is a BCBC and another BCBC could go into the X, and the Y would be empty. So there are 3 possibilities. Okay? So once you have ambiguity, of course, then you have the problem that there's going to be backtracking in such a system, meaning that you have search built in, and we have to account for that as well. Okay? Okay, now, traditionally, the way in which people make matchers is that they generalize on the idea of equality. Okay? And I'm actually not going to do that today, but I just want to, on structure equality, of course. And if you start with the traditional list-type equality tester between 2 lists, okay, what you have is that if A and B are pairs, then if the cars and cutters are equal, then it's equal, otherwise not. And alternatively, it's just not true, okay, unless they're both not pairs, in which case you test to see whether they're primitive objects that are equal. Like numbers, as if they were primitive. And what you do is you generalize that sort of thing. So you can put in some don't cares. Okay, you invent a thing called a variable. Okay, that's a don't care, but that's not very good enough. And you do further. You test that kind of idea, and then you start having them collect values. So you invent a dictionary that carries around the values. And I'm not going to go through this code. I'm just trying to say that's the traditional way to make a monolithic matcher. Okay. However, and that's more of it, more elaboration. However, the reason why I'm bringing this up today is because I want to show you a different strategy, a strategy which you may not be familiar with, and which is extraordinarily powerful, and we're going to use it for several different other things as well. Okay? And that is we're going to make some sort of combinators, which are the primitive matchers, which are programs that do primitive matching. And then we're going to make them have a standard shape so that combinations of those objects are themselves matchers. Okay, the combinations of those are in fact are compositions of programs. Okay, and this is going to be a way of extracting out the actual business end of the match, or the part that's doing the work, which can be compiled extremely precisely and carefully for any particular pattern. It can be compiled very well for any particular pattern, and in fact, sometime later, Chris may show you ways of compiling these things that involve pushing something through them tomorrow. Okay, but today, what I want to just show you is how you make a matcher this way. Okay? So what we're going to build is a family of combinators. And each of these combinators is some sort of specialist for a particular kind of match. Okay? Now as I said, this strategy is enormously valuable. One of the things that happens here is it's sort of a way of building a mix and match pile of useful pieces. Okay? And one of the crucial things to avoid doing when you make something like this is to prematurely optimize by thinking that you're going to pick out how many arguments you're going to need. You've got to look at the most general case first. But I'm not going to show you that in this today right now. We start from the simple things. So here's a device which is a procedure whose job it is to test whether or not something is a particular constant. I give it a constant somewhere in the history, somewhere in the past. It's going to give me now a tester for that constant. Okay? That tester I will use, and the tester has a standard shape. The tester is a thing which takes three arguments. A stream of data. Actually, it's a list of data. It could be a stream, and it wouldn't matter very differently, except that I wouldn't use words like car. Okay, but it gives me a stream of data, a dictionary, which is the mapping of the current values I know of all the variables from the variables, and what's called a succeed continuation. That is a procedure which you call when you get an answer, with the answer. Okay? Okay? And actually, tomorrow we'll also see cases where you need a separable fail continuation as well as a succeed continuation. Today. Or maybe today, really? Okay, today you'll see that. I'm sorry, I didn't know Chris was going to do that. But the crucial thing going on here is that this particular program, this little equivalence matcher, which is what I'm going to return as a value from the thing that I give a pattern constant, what I'm going to return as a value is the procedure that does this match. Okay, and if this procedure fails, it will return false. Also, if the succeed continuation it calls returns false, then this one will do something else. It will get back to here, and then this could do something else, and that's why this is valuable, because this is going to be a way in which we do the backtracking. Okay? So you're going to see this in a sort of interesting mechanism for building in an implicit search. Okay? So here's just some uses of this. If I make a matcher for matching explicitly the symbol A, that's what this is. Now notice that's in the procedure part, actually the operator part of an expression, a Lisp expression. Okay, so this is the value of this is going to be the equivalence matcher that derived from substituting the pattern constant for the word pattern constant for A for the pattern constant in here. Think of it that way, quote A. Okay, and then I'm going to give it a piece of data, a stream of data, which is going to have an A in it at the beginning, an empty dictionary, which is going to be an empty list here, because I'm violating an abstraction by telling you what the dictionary is made out of, okay? And the procedure list, which is going to just tell me all the values that came back. So it's a continuation. If succeeded, is show me what you get back, okay? The other thing you see here is a succeed continuation takes two arguments. One of them is the new dictionary, which in this case is going to be trivial, and the other is the number of things that have been eaten by this matcher out of the input stream, out of the data. So this is a way by which the segment matcher will be able to indicate what it found. Okay? What parts it snarfed up. Okay. Word from the Hacker's Dictionary if you don't know the word snarf. Okay. So for example, alternatively, so this match succeeded, and I came back with an empty dictionary, and I ate one thing, because it was one A right there, okay, and that's what it matched. If I try to match this, it won't match, because there's no A at the beginning. This is saying car, it's the first one, all it looks at is the first one in this particular kind of matcher, okay? So it says false. That's what it came back with. Okay, let's look at a more complicated one. This is one that corresponds to a variable. Okay, this is the matcher for a simple one-element variable. Okay? And so, again, it produces something of the same shape, given the variable name like x, which is what I'm passing in up here. That's really the variable name. Woo! I can't reach it. Oh, well, time for the unpleasant laser. Yes. Okay. I don't much like them because they make your hand shake, you see. I mean, the point is that light has weight, no mass easily. Anyway, so it returns, this procedure returns an element matcher, and the element matcher is a particular procedure which is just like the previous one you saw, which takes three arguments: a data stream, a dictionary, and a succeed continuation. Okay? And what it's doing is the following. It makes sure that there is something to eat. That's the and pair data. If there is, it checks to see whether I've got a value for the current variable yet in my dictionary. If there is such a value, I may have to check that it's equal to the one that I'm looking at. Okay? Otherwise, and if that's true, it succeeds, having eaten something. But if there is none already, it makes a new value in the dictionary, a new variable in the dictionary, which assigns the variable to the object in the data stream, the first object in the data stream, and also succeeds with the value 1. Okay? But if this equality test fails, or if either succeed fails, then this thing fails. The whole thing fails. And so here we have some examples. At the bottom of the page, there are 3 examples. If I want to match the variable x to a, b, and 3 in the empty dictionary and use the list as my continuation, then what I'm going to get back is a dictionary now containing a mapping of x to a, okay, and it says it ate one thing. However, if I then continue saying match the element x again to ba3 with the dictionary I just obtained, I get a false because the b is not equal to the a stored in the dictionary for the value x. Okay, and also if I finally, however, if I say x, I'm going to match this variable x against a3 with that dictionary, that does succeed and does not change the dictionary. Just showing you the simple versions first of things. Okay. But the important thing is that this object is exactly, this element matcher that you see here, the value returned, has exactly the same shape as the one you saw before, okay? As the equality tester for individual constants. Okay? Now we get to something with some real guts. Okay, this is can everybody see this? Let me push this out of the way a little bit. Okay, good. Okay, so here we have the segment matcher, and that's the one that has to be able to backtrack. We have to be able to backtrack into, so it can choose different pieces that might match. And again, I have a mechanism here, a combinator with 3 elements. Takes 3 arguments, which is what's returned. Okay. However, this is a little more complicated. Okay. Again, I want to make sure that what I have is something that has some data in it, okay, because I might want to collect a few elements, and I don't know how many. Okay, I'm collect a few. I may want to see if I've already got a value for this variable. I'll worry about that in a minute. Okay? If I have, and that's being tested over here. And if that's true, it's this whole section This is the consequent of knowing that I have some value already. But if not, if I don't have a value, this is let's get to the real case. I have a new segment. Then this material is the alternative where I have to deal with a new segment. And this is the interesting case. Okay? So what happens here? Well, I have a certain amount of data I can work with. Okay? It may be that if I try to eat a segment bigger than the data I work with, well, that's failure. Okay? So I certainly have to be dealing with only information that I have already. Okay? Now I have to pick out the length of the data I'm coming up with. That's n, and I'm going to start counting up how many things I can eat. Right? Supposing I eat 0 things, well, that's where I start. This is a little loop. It's procedure in scheme. It's a loop. Okay? If I is less than or equal to n, then I'm okay. Then I've got something to be done. Okay? If that's the case, then what I'd like to do is try out. So I'm going to succeed with the new dictionary, which binds the variable to the first I elements of the data. To the segment, which is the first I elements of the data, okay, in the dictionary. So I make a new dictionary based on the old one, which is got this first I elements attached to that variable. And I'm succeeding saying I ate I things. Okay? However, if a false comes flying back out of that succeed, okay, in other words, if something fails on the basis of the choice I made, okay, then I get to this or, which says, that was a false, in which case I go around this loop trying I plus 1. Okay, so I eat one more thing, okay, and try that. Okay, and if that doesn't, and if I eventually run out, then this is a failure. Okay? So of course this could have been written as and that this, but that's, people write their code however they please like that. So this is the essential little part that's doing the backtracking. Okay? I think that's fun in itself. Now this other thing is just something to make sure that I actually am matching the same thing twice. If I have if I have a value already in my dictionary, then I have to compare the data that I'm going to pick up, all of the n elements in it, make sure that that's actually those are there, and they're going to match piece by piece. And it's being done here by equality testing. Of course, it could have been done recursively by matching if I wanted to, but that's a different problem, and it would have been more fun, maybe. Okay, but it certainly wouldn't be obvious what's going on. This is barely obvious by itself. Okay. Anyway, so this is nice. And indeed, once you see this, then I have here just an example to show you. If I want to match the variable x against the list of things a, b, and 3 with the empty dictionary. Okay, this is in slide 14. Okay, page 14. And supposing I have a succeed continuation, which what it does is it gets a dictionary and the number of things that have been eaten, okay, and it prints those, it writes those out, and then it fails. So I get all the possible matches, because it will always fail. This is an always failing continuation. Okay? When that happens, I see that I get, 0 things eaten, 1 thing eaten, 2 things eaten, 3 things, nope, nothing worked. Okay? And so you see the backtracking occur. Okay? Now, why do I call this combinators? Okay, because of course there was a traditional world of combinators invented by Church and Curry and all those people. I suppose Schoenfinkel at the beginning in the 1930s. There were a bunch of logicians, and they were thinking of notations for representing all mathematical functions. They invented lambda calculus. That was Church and his friends. And the people in Germany invented combinators calculus. And the interesting thing is that they turned out to be the same, but they were isomorphic, I suppose. But the other interesting thing about that was that they did everything minimally. Not appropriate for an engineer. So they had basically 2 combinators, S and K, out of which they made everything, where S was S was a distribution of a function over two others, and K was dropping one of the arguments. And it turned out that that's sufficient for building all possible glue for mathematical functions. Okay, wonderful. Okay, now, great. Okay, so you make these exponentially long groups of S's and K's, and then some theoreticians of computer science, like David Turner in England, decided that they can make more efficient versions of combinators by adding a few more. Okay, and so they had C and I and things like that. But they're not, I don't think of that as being what I mean. I'm talking about making up ones that are appropriate for your problem, okay, and they're big and complicated things that do work. Okay? That's what supercombinators is. That's David Turner's paper. Okay? Yes. That was written in about 1982 or 81, something like that. Okay? So here's the real glue. Okay? Because lists are the things that glue things together. Okay? So here's the thing that matches lists. But what it does, it takes a bunch of match combinators for the elements of the list as its argument. It takes a list of such match combinators. Okay? And we'll see what this does. Okay? Well, indeed, it'll only eat lists. Okay? And what it does, it only actually eats a list, which is the first element, because a list is something it treats as a thing. Unlike, it's not like so it eats one thing, which is a list if possible. That's what this thing does. Okay? And see, it succeeds as one if it can. What it does here is it picks out a match combinator, and looking down these matchers, it tries the first matcher, okay? And if that matcher succeeds, it goes to the second one, with the data being the result of clipping off the first n elements of the input data. Those n elements are the things that were eaten by the first combinator in the list. Okay, and so that it just proceeds going around this loop doing that until and I'm always making a new dictionary on that basis. Okay, and then it's because what it's getting back is a dictionary from each combinator that's being used, and it uses that dictionary as the dictionary it goes around with. Okay.
Yeah, because at the beginning of your loop, your matcher is only being handed the very first element of the data stream.
That's intentional. I explained that. Okay, this is what's going on here is this object. It looks like a bug, but it's not. And again, this confused me for a long time. This thing is eating a list. The list combinator eats a list. It's one thing. It's the first thing of a data stream. Okay, that list is itself a data stream that may contain other things. Got it?
Right? Yep.
Okay.
This is an argument Jerry and I had several times over, and finally decided to agree that we didn't like each other's style.
Okay, it's a style. This is a style question of how I wrote it. Okay? Yes, Chris likes to write this in terms of pairs, Carcoda pairs, and I like to write it in terms of lists, but it doesn't matter. Okay? Okay. So anyway, this is the list combinator, and I think that this shows why these things. You see, with list combinator makes another thing which is exactly the same shape. Okay, so it can be used as a piece of something else. What makes something a good language in general is that you have pieces that, when you put them together, make bigger pieces of the same kind. Okay, so for example, TTL is a great language. Okay, TTL, the old logic families, like 74 LS whatever. Okay, those things worked real well because there were two bit standards that were interacting there that worked very well. One of them is a digital standard associated with it. I hear somebody also producing some FEEP. Okay, there was a feedback, but there's a digital standard there where the parts all knew about their voltage levels and things like that, and therefore could match each very well. Okay, and there was a standard family. But also, there's a physical family that came in dips on 100 mil centers and standardized numbers of pins, so that you could plug them in and you could make a thing that you understood would work the first time if you did it right. Okay, for slow speed things. Okay, but that's a kind of of power that makes, when small things turn into bigger things, okay, and the bigger things are of the same kind, then you can incorporate those into something bigger, and that's how you get abstraction, okay? It also happens, analog electronics is like this. You know, the things that have little legs, okay, you have resistors and capacitors and transistors, and combinations of those are networks which can have pins sticking out of them, which can be attached to other things. And so that's a good language, okay? And there are many things that are not such good languages, the things that people do in mechanical engineering, where they have to build gearboxes and so on, are much more difficult because they depend upon geometry. So you don't have it's not as clear what the standards are for making things hook together very well. If anybody's dealt with pneumatics, you know it's a disaster. Every possible fitting made by company X will not fit company Y. I've had this problem in building telescope parts. Okay, so using the combinators, the combinator glue for lists, you see here a slide which shows some examples. Okay, so if I want to match a list containing a constant A, a segment X, and a constant B, okay, and it goes to matching against the stream containing the list A, 1, 2, and B, okay. I'm just looking at Joe there because he was the guy who raised that. You got that right now. Okay, then with the initial empty dictionary, then X gets bound to 1, 2, and I ate one object, one list, okay, from the input stream. Okay, so that's how it works. If I, however, tried to match this against A, 1, 2, B, 3, that can't possibly match because there's nothing after the B, okay, over here to match that 3. Okay, so that produces a failure. Okay? Okay, now here's the neat thing. Okay? Of course, real compilers should be generic. This should not have a dispatch table written in it as an explicit conditional. You saw yesterday the advantages of not doing that. Okay, so I don't tie myself down, but I've done this here again because it fits on this slide. But you can imagine, but once you do it generically, you can extend it to any number of things you might want, which is the right thing to do. You might want to invent new kinds of matchers, new kinds of pattern match elements of various kinds. Okay, and here's particular ones. If I have an element matcher for a pattern, then I'm going to pull out the variable name. So here I'm just dealing with syntax, and I'm turning it into a set of combinators. This is the set of combinators, and indeed, if I have a list pattern, which is the compound 1, okay, then what happens here is I'm making a list combinator, which is the result of compiling all the patterns which are in the pieces of the list. Okay, I'll let you think about that for a few seconds. Okay. Okay, so here's an example. Of course, once I do that, then I have more complicated things I can write. So if I want to, so I don't have to write these combinators as combinations myself. Okay, I'm now showing you how you can compile a traditional pattern into a combinator structure. Okay, and it compiles very beautifully, and so these things do the right thing. Okay, to make that very simple. Okay, where did Chris disappear to? He's out there somewhere? He went that way. Okay. So, and here's an example of a complicated combination, the one that we started with. Oh, this time I put in the correct D because I ran it. Okay, as you can see. You see, when you run the program, you can tell whether it's right.
Unit testing.
Yes, that's called unit test, right? Okay, fine. I've learned that. Okay, so here's the A followed by any number of things called an X, followed by any number of things called Y, followed by any number of things called X, which had to be the same as this one, followed by a D. Okay, and indeed, putting in the problem that I gave originally, okay, you see that if I write out that it succeeded with a particular dictionary and a particular number of things eaten, okay, then I get 3 results. It's eaten that list, this list, which is the one list in the data stream, three different ways. It ate it with X being the empty object, X being the BC, and X being the BC, okay? Whereas Y had to eat the other parts, the leftover in the middle, okay? Okay, Chris, do you want to say anything between the time I'm, okay. So, because I want to make sure that I give you plenty of time. Okay? Okay, good. So now I'm going to lift this to rule systems, and I'm not going to show you all of the rule system because, of course, it's not very big. This kind of code is still only about 5 pages of real code, and it's all available. We're going to publish all this stuff somewhere for you because I do it for my class anyway at MIT. So here's examples of rules. Okay? So these rules are intended to go left to right. Okay, that is, they're intended to be, this is the pattern, this is some restriction that I can't necessarily write in the pattern, and this is the skeleton that's going to be instantiated. Okay? Okay, and so here's, and if this one has no restrictions, this one says that since the commutative law, I better be careful that there is some canonical ordering on my expressions, otherwise I can produce a very nice infinite loop. Okay? So that's what that's doing. And it's nice, commute, right? And the distributive law of multiplication over addition is the simple thing you see here. At least that's one direction of the distribution. Now, how do we deal with rules? So here's what a rule is. A rule is itself a program. It's a different shape program than a matcher, but it's going to use matchers as one of the things it does. And rules themselves may actually fail or succeed, and so something may care whether or not a rule failed. Okay, so the rule may want to, what's the right word here? The rule may want to have a backtrack into it and out of it into something else. That's what I'm going to say. Okay? So here's the thing which takes, for any particular rule, there are 3 parts. There's a matcher, which is a program compiled from one of those rules. I show you how matchers are compiled from the pattern part of the rule. I'm not going to show you how the skeleton is compiled from the skeleton part of the rule. It doesn't matter. It's something similar, actually a little simpler. Okay? But the restriction is compiled from the little primitive, the little predicate that you saw in the middle of the rule. Okay? But they're all 3 little programs. Okay? Now what I produce is a thing which takes an expression. And the thing which takes the expression can either succeed or fail on that expression. That's its job. Okay? I apply the matcher to the thing, the expression being put as the first element of a data stream. That's what's going on there, because everything I was dealing with in my matchers were data streams of elements. Okay, so it's matching one thing there. Start out with an empty dictionary, and if I get back a success, then the dictionary, then I get back a dictionary and a number of elements matched. I have to make sure that's one. It ate the whole thing, and only one thing. Okay, and I have to make sure that what I want to do is pick out the values of the variables from the dictionary. Okay. So I'm pulling out all the variables in the dictionary, and they happen to come out in some order, a canonical order. Okay. I'm not going to explain how that happens. If the restriction is not false, okay, then if there wasn't a none there, which happened to be the same as a false, okay, then I'm going to apply the restriction, and if that application of the restriction turns out to be also not false, then this passes, in which case I apply the instantiation, and that's the result, the value. But in any case, any one of these things, including the matcher itself, and the restriction or the instantiation, could fail. So it could say, I don't like this. Okay? And therefore this rule will fail. So now we're going to make these into packages of rules. So here's a very tiny little package. I'm going to make a rule simplifier, which is a list of rules. Again, these are being compiled by some process, which again, I'm not showing you the details of. Okay, but you saw the insides part of the compilation of the matcher parts. Okay, so this is itself a program, a rule simplifier, and this is going to be for a dumb little piece of algebra which contains only those 3 pieces of algebra. Okay, now how does this work? Okay, well, this is a wild piece of recursive code. This is the recursive controller. That is, you just saw the thing that makes rule simplifiers out of a set of rules. Sorry, you saw a call to it. You saw a call over there to rule simplifier, which takes a bunch of rules, a list of rules, and produces a simplifier, an algebraic simplifier. Okay? So the rule simplifier is going to return a program which simplifies an expression according to those rules. That's its job. Okay? Everything does programs that produce programs. It makes it a lot easier to program this way than almost any other style I know. I really love this kind of style where you have programs producing programs as values, or procedures as values. So the simplify expression procedure that's being returned here is one that says, let's simplify all the sub-expressions of the expression first. Okay? So I simplify all the sub-expressions. Okay? And there it is. That's what that is. And then out of that, I'm going to try all the rules from the rules that I was given. I'm going to try all of them on the simplified on the new expression, which is simplified all sub-expressions. So I'm going to be simplifying from bottom up. Okay? So that's what that's doing. And if that result is, if I get some result out of that, if I don't get a failure, okay, then I have to resimplify that result because it may have changed a lot of things. Okay, so there may be further simplifications to be done as a consequence of a simplification. Of course, a complication is what often happens. Simplifiers are not easy. Okay, and however, if it was just something that didn't match, the rules were irrelevant, then I have just the sub-expressions. So this thing goes buzzing around a little loop like this, simplifying all the sub-expressions and then simplifying the result of simplifications that are made on that. Okay, so it's sort of recursive in 2 different ways. It appears here and it appears here. Okay, and I think that may be a more complicated recursion than most of you have seen recently. Now, what try rules does is, well, it's doing something very simple. I have a little scan that scans each of the rules. If I run out of rules, then I fail. There's nothing to be done. But if I haven't run out of rules, well, if the first rule helps, if the first rule can do something, that's good. But if that fails, then I can just try the rest of the rules. Okay, and so what you're seeing here again is a thing that's, I can even back into other rules and things like that. Okay. Where's that? Oh, that's the end of this. That's interesting because I thought I had some examples. Oh well, okay. Actually, I do have some examples. I wonder if they're. I'm not going to touch a Mac. Okay, so it's time for a 5-minute break. Okay.
See what we can do.
And Chris, if you'd like to get ready, because you could have the rest of the time.
Yep.
Okay? Let's have a 5-minute break.